Over the past few weeks, we've looked at the layers of Earth, focusing on the lithosphere and the tectonic plates that make it up. We learned about the three types of plate boundaries: convergent, divergent, and transform, and the features that are made there. Now we're ready to look more closely at two of those features: earthquakes and volcanoes. Before you take these notes, it's helpful to review and preview by watching this quick video that's linked here. It's only 10 minutes long. I encourage you to watch that before you take these notes. So here's a quick review. We know that when plates move, they bump into each other, creating features like earthquakes and volcanoes. You can see a map here that shows all of the major earthquakes that happen within a 10-year period. Anytime plates move, you're going to get at least a small earthquake. You can almost trace the plates playing connect the dots. The orange area that's highlighted is the ring of fire. This is the area where volcanic activity is greatest, which also seems to coincide where earthquakes are the greatest. Coincidence? Let's see. An earthquake is any time the ground shakes due to movement of rock beneath Earth's surface. We know that the tectonic plates are in constant, albeit slow, motion due to convection currents in the mantle, so we are constantly experiencing at least small earthquakes on Earth all the time. Rocks undergo stress from all of that pushing and pulling, changing the shape of the rock. When we have convergent boundaries, they compress or push rocks together. Divergent boundaries stretch rocks apart, creating tension stress. And the third type of stress is called shearing, where the rocks slip past each other at transform boundaries. All of this stress can cause rocks to break. Anytime there's a break in Earth's crust, that's where pieces are moving past one another. We call this a fault line. There are three types of faults as seen here: a normal fault, a reverse fault, and a strike-slip fault. Each type of fault is going to be caused by a certain type of plate boundary, either convergent, divergent, or transform, and which causes a particular type of stress resulting in that given fault line. Let's look at these more closely. Strike-slip faults occur at transform boundaries where two plates are sliding laterally or sideways past one another. There's very little up and down motion. Think about poor California and the San Andreas Fault outside of San Francisco. This is where the Pacific plate is moving northwest and the North American plate is trying to slide southeast. These giant rough slabs of rock are trying to slide past each other, but experience a lot of friction. This builds up and builds up and builds up so much energy that is stored. Once it finally overcomes friction, the rock moves in one giant leap and the land along with it. This causes devastating, huge earthquakes like the one in 1906 that killed thousands of people and caused hundreds of millions of dollars in damages. Strike-slip faults are the most damaging and devastating faults in terms of earthquake damage. Normal faults occur at divergent boundaries where the plates are moving away from one another, so the rock is experiencing a lot of tension or pulling force. Unlike strike-slip faults, the breaks at normal faults often occur slowly over time and don't result in as many large earthquakes. The resulting fault will leave one piece of land lower than the other. In a normal fault, the rock that lies above the fault line is called a footwall, and the rock that lies below the fault line is the hanging wall. You can remember this by looking at the actual shapes of the rock. Can you see how the footwall has sort of a boot shape to it? These normal faults occur at divergent boundaries like mid-ocean ridges and rift valleys. The opposite of a normal fault is called a reverse fault. Tricky, huh? Not really. Whereas a normal fault occurs at a divergent boundary from tension, reverse faults occur at convergent boundaries due to compression forces. This stress is often responsible for mountain building over millennia, but in the short term results in movement of land and the corresponding earthquakes that come along with that movement. In fact, these are the forces that created the Appalachian mountain range that runs from Maine through our great state of New Hampshire and all the way down to Georgia. You can see here that there's again a footwall and a hanging wall, but now they're opposite, literally reversed in every way. The hanging wall is now above the fault line, and the footwall, still shaped like a foot, thankfully, is below the fault line. This is a great video to watch some really interesting footage on some of the world's most devastating earthquakes. A little bit dreary, but really interesting. You don't have to watch it, but it's a great one if you got some time on your hands. The next feature we're going to look at are volcanoes. We know volcanoes are created by tectonic action. So let's dive in a little deeper. We already know that volcanoes are often created from convergent and divergent boundaries. Let's look at convergent boundaries. If we have one plate subducting or diving down under another, that causes the gases trapped in the rock to escape as rock melts. Those escaping gases then explode through weakness in the crust, allowing lava to flow out onto the surface of Earth, sometimes violently, creating new land in the form of a volcano or a volcanic mountain. Remember to not confuse magma with lava. It's all about location, location, location. Magma is molten rock inside of Earth, below the surface, where lava is molten rock that's above Earth's surface. Still the same thing, just location is different. When lava cools, it will make new rock. The kind of rock it makes depends on the amount of different elements within the molten mixture. We'll look more at minerals and the rocks that they make in the next unit. Take a look at this volcano map. What do you notice in comparison with the earthquake map we saw at the very beginning of our notes? Do you notice there's a lot of similarities in the location of earthquakes and volcanoes? Let's look and see why that is. Like we saw on the map, volcanoes often form at the boundaries of plates because there's breaks in the crust that allow the magma to push through the surface. Most volcanoes occur at divergent boundaries or convergent boundaries that border an ocean. That dense oceanic crust carries tons of dead organisms and their gases. So when it dives down, those gases melt and evaporate. The escaping gases push up through the cracks in the boundary. However, there are also hotspot volcanoes that form far from plate boundaries. Go back and check out that map again. Look at Hawaii. It's in the middle of a plate. How in the world did it get there? And how in the world was that made? Divergent plates are most often found on the bottom of the ocean floor, so the volcanoes that result are typically not seen by us. They're deep underwater. However, there are a few places, like in Iceland, where the volcanoes have built up so much over time that they've risen above the surface of the ocean. In fact, you can visit Iceland and the active divergent boundary there to see the new land being formed. It was a 2010 eruption, actually, in Iceland that caused major airline cancellations for days and huge impact on farming due to the heavy ash that the typically quiet divergent boundary volcanoes spewed into the skies. It went as far west as Canada and as far east as Eastern Europe and caused a lot of trouble. Volcanoes also occur at convergent boundaries, where oceanic crust and continental crust meet as previously discussed. But they can also happen where two oceanic plates collide. The older, denser oceanic plate will subduct or dive down and burst through cracks in the newer oceanic crust, sort of like along perforated paper, resulting in a string of volcanoes formed at the same time called an island arc. This is how places like Japan and the Aleutian Islands off the coast of Alaska were formed. You can even see how the Aleutian Islands almost trace that oceanic plate boundary. The trickiest of volcanoes are called hotspot volcanoes. These often lie in the center of plates far from any plate boundaries that could explain their origin. We know that they're not a result of subduction or diverging plates and seem to have a stream of magma like a blowtorch melting the crust from deep below. As plates move slowly across this steady blowtorch, it continues to produce volcanic mountains in a chain. This is how Hawaii was formed and why more islands will appear next to the current islands in the next several million years. In fact, there's a new island called Loihi Seamount that will be Hawaii's next island. Seamount means it's underwater still. The peak is still over 3,000 feet from reaching the surface of the ocean, but it appears to be growing slowly over time from this hotspot phenomenon. Still, much is unknown about hotspot volcanoes, so you guys need to grow up, become geologists, and then come back and teach my class when we have more information. Regardless of how or where they form, all volcanoes have a few features in common. They really begin and are fueled by the magma chamber, which is a pocket of boiling molten rock below the surface. The pipe that goes up the center is the path that connects the chamber with the surface of Earth, in addition to side vents that also release gases and lava. The lava flow is the area that is covered by the lava as it explodes or pours out of the pipe and vents. Especially when there's a more explosive event, you'll see a crater at the top that often forms around the central vent. This enlarged bowl-shaped opening is the result of such extreme temperatures as the lava pours out. Because the ingredients are different in different kinds of lava, some lava is stickier, some lava is more liquidy and flows more easily, and will result in different shaped volcanoes, whether you have a very flattened curve like a shield volcano or more of a cinder cone volcano, which is very tall. The shape of a volcano is determined by the kind of lava that pours out. You can see here the different features of the volcano that we just talked about. Make sure you label your diagram. You don't need the whole definition below, just the red words. Finish that up beautifully and you're done. Great job. See you guys next time.